Okay, so at the end of the last video, we had just finished defining cardinality and kind of extending our definition of cardinality to the more mature definition that will be used. This will extend even further. This will extend to any set. But right now, we've just defined what it means for a set to be finite and for a set to be countably infinite. And then if you're finite and countably, or if you're finite or you're countably infinite, either way, you're countable. And the idea, more or less, is just a formalization of the idea that we can count it, right? So, I mean, we're counting in this formal way of defining bijections, but and a bijection used in this particular context is called an enumeration. But what an enumeration fundamentally is just it's a comprehensive way to list out the elements of A one at a time. You're not allowed to say any of them twice, and you're also not allowed to skip any, but in such a way that I could kind of go down the list like 1, 2, 3, 4 and get everything. I have to assign 1 to something, I have to assign 2 to something, I have to assign 3 to something, and in that way, if I've done that assignment, then I've defined a way to count. I can say that this is the first one, this is the second one, this is the third one, etc. And that's really what we're doing. So what we're going to do now is a bunch of examples, kind of building up to the big thing that I want to show with all of this. So we'll start real small. What is the cardinality of n? Well, clearly the function f defined by f of n equals n is a bijection, just the identity function. Thus, by our definition, that means that the cardinality of the natural numbers themselves is, of course, omega. Of course, the fundamental kind of thing that you use to count, is countable. So the cardinality of n is equal to omega by our definition. Or if you'd like, technically, I think most people would probably write this aleph naught, but we're just going to write omega because we're not that fancy. My handwriting is not good enough for me to make the work look good, so there's no point in writing the nicer symbol. So yeah, obviously the cardinality of the natural numbers is omega. Is the cardinality that this is almost basically saying the cardinality of the natural numbers is the cardinality of the natural numbers. Let's look at another set though. What about z? So I'm not sure if I've formally defined z. This is the integers. And specifically, it's basically the natural numbers, but along with 0 and all the negatives. So you got dot, 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 -3, -2, -1, 0, 1, 2, dot, dot, dot. This is the, I guess I should add 3. This is the integers. What's the size of the integers? Well, we're going to claim that the size of the integers is equal to omega as well. It's actually the exact same size in this sense as the natural numbers themselves. So why? Well, we can list out what we need to do is define an enumeration. So that's what we did. That's what we did here up as well with n. F of n here is a bijection, but I really should have written an enumeration. And an enumeration, we've defined it very formally, but it is exactly what it sounds like. It's just a way to list out the elements. So we just need to figure out a way to label everything in order. So I need to kind of define a first thing, a second thing, a third thing, and get everything. So we can list out all of z in this way. So I can basically say, what's the 0th guy? Well, I'm going to declare that to be 0. What's the first guy? I'm going to say that 1 is the next one. So I'm going to assign 1 to 1. And then what I'm going to do is I'm going to say, well, what about -1? That's actually going to be the second. And then I'm going to declare the third thing to be 2. Let's go to 8. So the fourth thing is going to be -2. The fifth thing is going to be 3. The sixth thing is going to be -3. The seventh thing is going to be 4. The eighth thing is going to be -4, and so on. And so I just alternate the negative and positives of everything. And so, this doesn't look like a function in the way that I've been defining functions, but of course it is, right? I'm declaring, like, what I mean by all of this is, f of 6, for instance, equals -3. So I've defined a function here in this way. I've defined f of n to be, this is a comprehensive, like, dense definition of n, and it lists out everything. So, I'm counting. You can see what I mean by counting. I just have to I have to be able to count them one at a time in such a way that I get everything. And you can see the biject. So hopefully you can see that this is a bijection. Hopefully it's clear. This is an enumeration. And that's it. That proves that the cardinality of z is omega. I've proven that it's countable by counting, by finding a way to count it. So, let me just kind of write that. I'm counting. All the formalization of the last video was basically just building up to this, building up scaffolding so that I can do stuff in this way and just kind of say, I'm counting. In a sense, I've defined an algorithm for listing out all of z. One at a time. If I let this go on forever, I won't miss anything. Let me write that down. If I let this pattern go on forever, I won't miss anything. Not only that, everything will appear eventually. That's kind of the big deal. That's kind of how you would prove formally, more formally than I'm doing now, like why this is a bijection. You can kind of just say, well, what if I want 45, right? I can tell you where number 45 would come in, and I can tell you where that number would appear on this list. And it would appear after some. If I had a computer just list these out one at a time, I would only have to wait a finite amount of time in order for that number to appear at some point. Every number appears after a finite amount of time, if you want to think of it that way. So I'd eventually hit anything. That's kind of a better way to say it, but I've already written something down. So that's the integers. Let's do a simpler. Let's do one more finite set. Here's another example. Let's look at an alphabet, such as the Roman alphabet or the English alphabet. What's the cardinality of this guy, sigma? Well, it's obviously 26. Why is it 26, though? It's because I can kind of do this assignment. A is assigned to 1, B is assigned to 2, C is assigned to 3, and so on until Z is assigned to 26. And I say A is assigned to 1, but it's just as valid to say 1 is assigned to A because it's a bijection. It's a two-way street. It's a one-to-one correspondence. That's why we call it that. I'm just identifying C as the number 3. Here's another example. What about sigma squared? And what I mean by that is sigma cross sigma, the set of all ordered pairs of 2 letters. You can kind of think of these as strings of length 2 if you want. What do you think it is? Well, it's obviously 26. What's 26 squared? I'll let you kind of think about why yourself, but it's pretty obvious that that's 26. I've talked about that in an earlier state. Let's do something a little more challenging. The reason I wanted to write this down is because what I'm about to write down is a little more surprising. So note that this is greater than actually sigma, right? If I square this finite set, if I take the product of this finite set with itself, then the cardinality of that is explicitly bigger than what it was before. Let's compare that to this guy. N cross n. So it's the pair. It's the Let me actually erase this. It's the set of all n m, such that n and m are in n. So it's the set of all pairs of 2 integers, or 2 natural numbers, excuse me. Um, believe it or not, n cross n, the cardinality of it, is equal to the cardinality of n. It's equal to omega. It's actually the same. It's not bigger at all. Why? So, I mean, sometimes this surprises people when they first see it. It's something I've seen so much at this point that I'm just used to it, but maybe this is surprising. I'm not sure if it is. Let me know in the comments if you find this result surprising, that the product of n times n is actually no bigger in cardinality than n. So let's do the proof. And this proof is really important. Really try to pay close attention to what I'm going to do here. So we can list everything in a table like this. So the table is going to look like, I want this to be moderately big. So I'm going to basically make this a 1, a 2, a 3, a 4, a 5, a 6. I'll make this a 1, a 2, a 3, a 4, a 5, a 6, dot, 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 dot. So basically in the table, you know, any cell in the table is obviously going to correspond to, like, for example, this grade right here, this would correspond to 2, 4. Right, and then this guy right here, this would be 2, 2, etc. And I'm not going to list all of I'm not going to write them all down. Instead, I'm just going to write points. But you can understand what the points mean, hopefully. So, whoops. Come on. So I'm just going to draw some dots. I'll skip ahead to when these dots are drawn out. All right, so I've drawn out the kind of all the grid, if you will. And remember, each of these points represents a pair. So for example, this guy right here, that's 4, 5. This guy right here, that's 5, 5, etc. So I can traverse the table like this. So can traverse this table. Here's how I'm going to do it. I'm going to start here. So I'm going to start with 1, 1. Then I'm going to go to 1, 2. And what I mean by this line here is that, you know, I'm starting with 1, 1, and then I'm going to go to 1, 2. And I'm going to, so this is the first guy. This is what I'm going to assign to 1, and this is what I'm going to assign to 2. And then I'm not going to write them all out, obviously, but that's what I'm going to do it. Then I'm going to go to this. I'm going to go to 2, 1. Then I'm going to go to this, actually. And what I'm going to do from there is I'm going to go like this. Then I'm going to go here. Oops, let me try that again. And I'm going to go down again. And then I'm going to go like this. Oops. And I'm going to go down again. And I'm just going to keep doing this. I just kind of go down of the what are called the off diagonals, all of them, one at a time, essentially, and then, you know, dot, dot, dot. Just go like this. It's clear that if you do this, you eventually get everything. Clearly, this eventually hits anything. And so just to make sure people are clear, you know, basically what's going on is 1, 1 is 1, 1, 2, whoops, is 2, and then 2, 1 is 3, then 1, 3 is 4, and then 2, 2 is 5. And it's kind of interesting because you can see, you know, writing out what I actually just defined here. Clearly, I defined a bijection. I hope nobody is confused by that. But if a teacher were to just write out this pattern one at a time, it's kind of a hard pattern to discern. You kind of have to see it visually. But it makes perfect sense visually. This works. And this is called something. This has a name. This is kind of a traversal method, and it's called dovetailing. And it's actually going to prove very useful in multiple scenarios for us. So remember the name, dovetailing. Dovetailing is when I kind of traverse a two-dimensional table of discrete points in this way. It's going to be very, very useful. And then what I can do is this actually, from this, it's actually the case that n to the k for any k. If I take n cross n cross n, let me just start with that maybe. Oops. Is also equal to omega. It's always countable. I can keep going. N to the k is always countable for any finite k. And the reason for that is that I can just basically use, now that I know that I can count n squared, I can just put n squared as the x's, and then pair those with, so basically take the list, if this is the first guy, this is the second guy. What I can do now is essentially I can just do this. Let me maybe just write it out. Right, instead of going like that, what I can do is I can say, put a 1, 1 here instead. Put a 1, 2 here instead. Put a 1, 3 here instead. Put a 2, 2 here instead, etc. Just use the countable set that I had before, list that down here, and then clearly, this point, for instance, represents this point here represents the point 1, 1, 2. This point here represents the point 1, 2, 4, and so on. And so this gives me all the triples in the same way. I just kind of redo it using the, just kind of piggybacking. So, by induction, I guess, is really what you would say. And I'll explain what induction is later. But yeah, I mean, it works. I can just keep repeating this and get that this is true, actually, for any finite k. So that's kind of interesting. The next one, let's do another one. The rationals. I can do the rational numbers like this. So the rational numbers, we think people forget what they are. You denote it q, and it's actually the set of all a over b, such that a and b are integers. It's the set of all ratios of two integers is what the rationals are. This is also countable. Why? Well, we can kind of use everything we can use kind of everything we've done so far. Start with q plus equals the set of all a over b such that a and b are in n. Let's just start with all the positive ones. First of all, we can define a couple of bijections. So first, start with the association a over b is going to be associated with ab, the ordered pair ab. This is a bijection. This is a bijection. It's a bijection from q plus to n squared. And since we already know that n squared is countable, that means that q plus is countable. Because remember, bijection, having a bijection is what we use to say how we define size. So obviously then, by above, we have that the size of q plus is equal to the size of the natural numbers squared is equal to omega. And then, since that's the case, then so we've numbered them this way, and then we can basically arrange them alternating negative and positive in the same manner as when we showed that z was countable. Once I've gotten the positive side, I can get the negative side and count them both at once just by kind of doing this alternating pattern that we did originally up way up here, right? I get all of q plus, and then I can get q minus in the same way, and then I can just combine, and then I can just kind of weave those two bijections together in this manner. And so there's some formalism that I'm skipping over, but I don't think that it's that important. I think you get the idea. I wanted to write out the formalism so you knew kind of what the formalism would be, but I don't think it's complicated. I don't think I actually need to like be very careful with it. I think people get what I'm talking about. And you can see that these little facts, these little observations, really build us a kind of effective repertoire of ways to count things cleverly. So before we bring this back to Turing machines, let's go ahead and state some facts that are kind of obvious about cardinality, just kind of for the record. So if F maps A to B is injective, so we don't have a full enumeration, we just have an injection, then the cardinality of A is less than or equal to the cardinality of B, which we kind of observed already, but we can prove it. And we won't prove it. I'm sure it's kind of obvious. It was kind of how we got to the definition of cardinality in the first place, but it's worth writing down just for the record. If F maps A to B is surjective, that is onto, then the cardinality of A is greater than or equal to the cardinality of B. Some things I haven't kind of stated yet or observed. If A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B. That should be obvious too. Some other things. If the cardinality of A is equal to n and the cardinality of B is equal to m, then the cardinality of A cross B is equal to n times m. Also, if A and B are disjoint, then A union B, oh my god. Yeah, also if A intersect B is 0, if A and B are disjoint, then the cardinality of A union B is n plus m. In order for this to be true, they have to have nothing in common, though. Otherwise, this wouldn't necessarily be. So now let's connect this back to Turing machines. And when I say Turing machines, I mean let's actually consider alphabets. So consider any finite or countable or even countably infinite, but we're used to working with finite. Alphabet. For instance, the Roman alphabet, A, B, C, Z. Let's recall something. So let's recall that sigma star is equal to the set of all finite strings. Of characters. Let's think about the cardinality of this. We obviously know that the cardinality of sigma is 26, but what's the cardinality of sigma star? It's obviously infinite, but is it countable? So we claim that it is. So how could we do this? So we need to enumerate every finite string. So the way we'll do this we're going to use something called the dictionary ordering. Sometimes it's known as the lexicographic ordering. In fact, that's pretty much what people normally say, but sometimes we call it lexicographic. Okay, so what are we going to do? So first of all, let's start with one-letter words. So start with one-letter words. So that is, I'm going to say that A is 1, B is 2, C is 3, dot, 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 Z is 26, just like before. We're going to start with one-letter words. Now we're going to move on to two-letter words. So how are we going to do that? Well, my computer is very unresponsive at this point. Okay, so I'm going to call this one, I'm going to start with AA. And so this will be like the 27th letter, AA. Then I'm going to go to AB. Then I'm going to go to AC, dot, 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 up to AZ. So this will be the 26th, this will be the 52nd letter, 52nd word, I mean, AZ. And then I'm going to move on to BA, and then BB, and then BC, and then dot, 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 up to BZ. And then I'm going to have CA, and then down to CZ, and then dot, 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 going this way, and then ZA, ZB, down to ZZ. And so what'll be this, what numbered string is ZZ? Well, it's actually the 26 plus 26 squared ith string. So whatever 26 squared plus 26 is, that's the number I'm at. And now I think you see where this is going. Let's move on to three-letter words. Now three-letter words. So now I'm going to go AAA. So this is 26 plus 26 squared plus 1. Now AAB all the way to A. And now I'm going to kind of condense it. I'm going to do the same. I'm going to do the exact same thing I did up here, except with two-letter words. So I'm going to go all the way down in the same way I did before, up to AZZ, and then I'll reset it again. BAA down to BZZ, and you know how to do this because I did it up here. And then it goes all the way to ZAA down to ZZZ, and so this is number 26 plus 26 squared plus 26 cubed, and it keeps going like that, and continuing like this. Continuing like this enumerates all of sigma star. So one thing I want you to note before we move on is it's pretty important to note we can easily construct a Turing machine which will do this for us. That is, a Turing machine that will just kind of one at a time on some tape print out every single possible string, maybe separated by a space. This is a very algorithmic process that I've described here, and I haven't spelled it out explicitly, but hopefully you can believe me that you can easily construct a Turing machine which will list this out, which will do this for us. That's a pretty important thing to observe for later. Also recall, and this is the big kind of punchline for this video, I suppose. Every Turing machine M, remember when we made a universal Turing machine, we figured out how to describe completely any Turing machine with a finite string. Be described by a finite string over the alphabet. Sigma U was 0, 1. It had a bar, it had this guy, it had a parentheses, and it had a comma. So that was our alphabet for the universal Turing machine. And we figured out that we had a standard way that we could write down a string, and that string would represent a Turing machine. It was a unique function from strings to Turing machines, essentially. So because of this, if every Turing machine can be described by a finite string, then and the set of all finite strings is countable. So since the set of finite strings over sigma u star, well, it's just sigma u, is countable, it follows that the set of Turing machines is countable. It's also countable. And then from that, we can say, also recall, so maybe I'll box this. So we can conclude now that the set of all Turing machines is actually a countable set. And then more importantly, also a decision problem is computable. What was our definition of computable for a decision problem? A decision problem is computable if and only if there is a Turing machine which describes it. Which, I'm sorry, decides it, I should have said. Thus, there are no more computable decision problems than there are Turing machines. Thus, the set of all computable problems is countable. Set of all computable problems is countable. And we can kind of formulate that in a specific way. Remember, R is the set of all computable problems. So we can kind of turn this into we can kind of say now that R is cardinality omega. And now let's compare this to the set of all problems. We'll fix our standard unary alphabet. So we'll fix an alphabet. We'll fix the alphabet for all computable problems to be 0, 1. So in other words, every decision problem is a collection of finite strings over this alphabet. So decision problems are, by definition, subsets of 0, 1 star. Meaning that, so set of all problems is exactly this. Remember, I use the name all for this class, but it's the power set of 0, 1 star. It's the set, it's the set of all subsets of finite strings. This is the collection of all finite strings. The set of all subsets of finite strings, which is exactly what decision problems are. They're subsets of finite strings. They're collections of strings over some alphabet. And so the collection of all languages really is the power set of 0, 1 star. So this is that. So in order to compare the set of all computable problems in size to the set of all problems, period, we need to really figure out what this is.